Welcome to the next video in the mathematical logic sequence. We're talking about propositional logic and in this video, recursion. Okay, so recursion is really not very different from induction, and one of the main things that separates them is that we just talk about it as recursion when we are defining a function rather than merely defining a set like an induction. Like with induction, when we do a definition by recursion, we start by declaring an initial value. And for us, that's going to mean the value of the function evaluated at 0. So in this completely arbitrary example, I have defined f at 0 to be 2. So 2 is going to be our base case, or right, the value in the base case. Then there's going to be a rule taking us from earlier cases to later cases. And that's going to be this sort of recursive part. I define f at n in terms of, now importantly, two ingredients. There's the earlier value of f, which we're writing as f of n minus 1, and there's the earlier input, which I'm calling n minus 1, right? So you actually have both ingredients that you are free to use when you are defining a function by recursion. And so I wanted to pick this example to show you both of them coming up in this example. So that's why I somewhat arbitrarily picked it to be this, just for demonstration purposes. Now, so here what I'm showing on the slide is on the right-hand side, I'm showing the particulars of this example, and on the left-hand side, I'm showing the symbols that we will use to talk about them in the general. So while here, this particular example, I'm writing as little f, in general, we will write big F for the function that is being defined by recursion. Here, my sort of initial value is 2. In general, we will write that as z sub naught, or z naught. And then there's this set z, which I haven't really displayed in this particular setting, but it might be easier to first talk about this function g. Now, g, in my example, is the plus function. G is a two-place function, typically, and the left coordinate is typically supposed to be the earlier value of f. So you can kind of see that here, right, my function g is the plus function. The left-hand side is the x, and that is the earlier value of the function. The right-hand place is supposed to be the earlier input value, in this case, n plus 1. So that right-hand coordinate, y, is, I am taking that to be n plus 1 in this example. So that's the function g, right? Effectively, g is the function that we are using to determine the next value of the function based on the earlier value of the function and the input. So, right, so g is the function that is doing the definition for recursion, right? In this example, g is plus. Now, because the left coordinate is always the outputs of the function, right? Because it's always what the function returned on the earlier input. So the left coordinate of g needs to be, right, the domain needs to be some set made up, containing all of the values that the function takes. So that's what z is, right? So you can see that I started z off at 2 because the smallest value that the function takes is 2. And over here on the whiteboard portion, I've computed the function f on a few different values, partly to demonstrate how you compute f using recursion, but also it demonstrates that the next value, so to speak, for the function f is 3. And that sort of explains why I wanted to have 3 in this set z, because it's one of the values that the function takes. And then also I want to have 5. So 5 is going to be in this set also. Now you can see, and especially since it's pretty clear that this function is an increasing function, this function is never going to take the value 4, so I could have omitted 4 from z. But it also doesn't hurt to leave it in, and it's just easier to describe the set as the numbers 2, 3, 4, and so on. It's a very simple description, and it will contain all of the values that the function ever takes. So that's a good choice of z, right? I could have chosen a smaller z, but this one works and is easy to describe. So that's why I took it to be this particular choice in this example. So anyway, so z is the domain of the left coordinate for g, and the right coordinate for g, right, because it is supposed to always be these earlier inputs to the function, but hey, the inputs to the function are just natural numbers, so the right coordinate of g is supposed to be the natural numbers. So the domain of g is z cross the natural numbers, and the range of g is supposed to be z again, because after all, right, the return values, the output values, that the values that g takes are what define f on the next input. So since z is made up of the image values of f, then that can also serve as the range for g, because the image values for g are also the image values for f. Next, we'll describe the recursion theorem. The recursion theorem is, in a sense, kind of trivial, right? It sounds very sort of noble, and I guess maybe it is. But what it states is really fairly simple and straightforward. It says that whenever you specify this z naught, the initial value, and a z and a g, right, when basically the ingredients for recursion, whenever you specify the ingredients for a definition by recursion, that determines a unique function, basically telling you that you can define functions by recursion, that when you do, you get a well-defined function. To really spell things out, then, the recursion theorem really is made up of three components. It's going to tell us that these numbers that we use to define f are unique and well-defined. So that's going to be this part, right? It says that for each n, there is a unique number z sub n with the following property, that it has this sequence z naught up to zn, such that every next value, right, every next z value comes from plugging these things in for g in the previous coordinate. And we use this to define what f of n is for each n. So that's the first part, right? This is effectively just telling us for each n, the number zn is uniquely determined, meaning that by defining f in terms of those numbers, we are getting a well-defined function. So that's what the first part is telling us. The second part is telling us a fairly straightforward fact about f, which is that at 0, it takes the value z naught, and that for any next input, it is determined by g on the earlier inputs. Now, this whole thing is going to be completely trivial, because, right, the proof of this is, well, f at 0 is equal to z naught just by definition. That's that, right? That barely needs a proof at all. I mean, it really needs no proof at all. And then this part is true, again, just by definition, because we define f of n to be z sub n, and z sub n, after all, from this earlier part, is g on the, earlier components. Okay, fine, the z sub I is, we have to kind of remark that, or sort of make the case that z sub I is equal to this f on n. But that just comes from the inductive case when you do this proof by induction. So in any case, it's a fairly trivial proof. And so I'm really not even going to give the proofs for these two theorems, because they are, right, you basically just write out the proof by induction in both cases, and the claims are just satisfied immediately. So it really takes no work at all to do these proofs by induction, and so I won't bother with them. There's a third claim in the recursion theorem, which is that the function, right, any function satisfying the properties claimed in part 2 is uniquely determined, right? So we're not only saying that f has these two properties, this big F that was constructed by recursion, but also if you took any other f prime, which also had these properties, that is to say, f prime at 0 is z0, right? This f prime is this other function which also has these properties. And f prime at n plus 1 also is g of f prime at n comma n, right? So this being that, f prime has this property just like f does. Then we're going to prove that f prime equals f. And this one I'll talk about the proof a little bit. Okay, so we're going to prove that f is unique by imagining some other function f prime, which also has these properties. Sorry, I am seeing that there is a typo and that this should be f prime. But just imagine there's an f prime there instead. So the things that we're going to assume about f prime is that at 0 it's equal to z naught, and at n plus 1 it's equal to g of f prime of n comma n, right? And what we hope to prove is that f is equal to f prime. We're going to do this by induction. And our base case is where n is equal to 0. But there we're trying to prove that f at 0 is equal to f prime at 0. That's immediate because both of them are equal to z naught just by assumption. For the inductive case, we assume that n is some number greater than 0 for which the claim holds. Actually, I think that should be a greater than or equal to 0. Sorry about that. So that should be a greater than or equal to 0. And now we want to prove the case or the claim for n plus 1. And I see that the text has gone off the screen, but this is just f prime at n plus 1. Right, and the proof is just completely immediate, right? If we look at f of n plus 1, we know about it that it has this property that it's equal to g of f of n comma n. And our assumption from the inductive hypothesis is that big F of n is the same as big F prime of n. So then you get this equality. And then from our assumption about the properties of f prime, you get this expression right here turns into f prime of n plus 1, and we're done. That proves this claim by induction.